In this section, we discuss what happens when light impinges upon the surface between two transparent materials. Here we see a beam of light striking the interface between air, which has an index of refraction of n1 equals to 1.00, and glass, which has an index n2 equal to 1.33. When the incident beam strikes the surface, it splits into two beams, a reflected ray and a refracted ray. If we draw the normal to the surface, the angle θ1 that the incident ray makes with respect to the normal is called the angle of incidence. The reflected ray departs at that same angle, θ1, so that the angle of incidence equals the angle of reflection. As long as the incident ray does not strike normal to the surface, meaning that the incident angle θ1 does not equal 0, the ray that penetrates through the surface bends away from the straight line path of the incident light. This bending is called refraction, and the ray that passes through the surface is called the refracted ray. The refracted ray makes an angle θ2 with respect to the normal. Note the reversibility in the direction of the light. Light impinging upon the surface from the opposite direction would follow the same path. The direction and degree of deviation of the refracted ray from the straight line path of the incident beam depends on the indices of refraction of the two media. If the material into which the refracted beam travels has a larger index of refraction than the medium from which the incident beam arrived, then the refracted beam is bent toward the normal, and θ2 is less than θ1. If the incident beam approaches the air-water surface from below, the incident beam again splits into two parts at the interface, a reflected ray and a refracted ray. And the refracted ray, now in air, bends from the straight line path of the incident ray. In other words, it refracts, with an angle θ2 with respect to the normal. This time, however, it bends from the straight line path in a direction that is away from the surface normal, a consequence of the beam going from a material of larger index to one of lower index. In general, the light bends towards the normal when going from a lower index to a higher index, and away from the normal when going from a higher index to a lower index. However, this notion can be expressed more quantitatively through Snell's law, which states, when light travels from a material with a refractive index n1 into a material with refractive index n2, the refracted ray, the incident ray, and the normal to the surface all lie in the same plane. The angle of refraction, θ2, is related to the angle θ1 by n1 sine θ1 equals n2 sine θ2. This is called Snell's law. As a quick example of its application, let's suppose that light impinges on the air-water surface at an angle of 58.0 degrees. What is the angle of the diffracted ray, θ2? We start with Snell's law and solve it for θ2, giving θ2 equals sine inverse of n1 divided by n2 times sine of θ1, where n1 equals 1.00, the index of air, and n2 equals 1.33, the index of water. Plugging in the numbers, we find that the refracted angle θ2 equals 39.6 degrees.